Previously, we covered the core foundations. Now, in part 3, we tackle Mercury, interior and core. In the last episode, we looked at Mercury's surface, a battered, ancient landscape shaped by billions of years of impacts. Today, we're going underneath it. Here's the question driving this episode. How does a planet the size of Mercury end up with a core so large it defies easy explanation? And why does that matter for how we understand rocky planets in general? Act 1. What's down there? Mercury is the smallest planet in the solar system. Its diameter is roughly 4,180 kilometers, just over a third of Earth's. You'd expect a small planet to have a proportionally modest core. Mercury doesn't. Its iron core is estimated to span around 3,600 kilometers in diameter. That's roughly 85% of the planet's total radius. Earth's core, by comparison, accounts for about 55% of our planet's radius. The difference is significant. So here's the open question I want you to hold on to. If Mercury is so small, why does it have so much iron? We'll come back to that. Sitting on top of that core are the outer layers, a relatively thin silicate mantle, and a crust above it. Early estimates put the mantle at around 500 to 600 kilometers thick, though data from NASA's Messenger spacecraft helped refine those figures considerably. Messenger orbited Mercury between March 2011 and April 2015, the first mission ever to do so. Act 2. What Messenger told us before. Messenger, direct data from Mercury's orbit, was essentially non-existent. The only previous visitor was Mariner 10, which made 3 flybys between 1974 and 1975 but couldn't stay. Messenger changed that entirely. It confirmed something unexpected. Mercury has a global magnetic field, weak, only about 1% of Earth's field strength. But it's real. A magnetic field of that type almost certainly requires a partially molten, convecting outer core. That's not a trivial finding. It tells us Mercury's interior is still active at some level. The planet hasn't fully solidified. Something is still moving down there. Messenger also measured Mercury's bulk density at around 5,430 kilograms per cubic meter, remarkably close to Earth's uncompressed density, and far higher than you'd expect for a planet this size. That figure is direct evidence of just how iron-rich Mercury truly is, which brings us back to that open question. Act 3. The iron problem. There are a few competing hypotheses, and none of them is fully settled. One idea is that Mercury formed from iron-rich material naturally concentrated in the inner solar system. Close to the Sun, temperatures during the solar system's formation may have favored metallic iron over silicates, so Mercury simply accreted from what was available. A second hypothesis involves a giant impact, not unlike the collision thought to have formed Earth's moon. Hit Mercury hard enough, early enough, and you strip away much of its outer silicate layers, leaving an iron-dominated remnant behind. There's a third idea involving solar wind erosion of the early mantle, though most researchers consider this the least likely of the three. The honest answer is we don't yet know which process dominated, or whether it was some combination of all of them. Bepi Colombo, the joint European and Japanese mission currently en route to Mercury, with arrival expected in late 2025, is designed in part to tackle exactly this problem. What we can say with confidence is this: Mercury's interior is not the simple, cold, dead shell you might expect from the smallest planet in the solar system. It's geologically complex, partially active, and it raises genuine questions about how rocky planets form and evolve, questions that go well beyond Mercury itself. Next episode, we look at Mercury's exosphere and orbit, including why a planet with almost no atmosphere still technically has one. The full Mercury playlist is linked below. And if you're finding these episodes useful, subscribing is the simplest way to stay with the series. That is part 3 of Mercury. In part 4, we explore the next key question. Subscribe so you do not miss it.